So in case anybody's just joined remote, we're going to just give it another minute or two because this is a nicely hidden room in the building. It is, yeah. You can leave all your belongings here afterwards. It'll be fine. Oh, did I? Well, thank you. Okay, I guess we go. So good morning, and whatever time zone you're in, relevant greetings. My name is Stephen Farrell, and Jonathan is on a not gigantic screen this time, but is my co-chair of the Usable Formal Methods Research Group. So welcome. We have a slides clicker that seems to work. There's a note well. This is the IRTF, but it follows the IETF's IPR regime, so you should familiarize yourself with that. There's recordings. You can go and enjoy them later on. We have a privacy and code of conduct. You should be nice to each other, and let's keep doing that. And just to point out that the IRTF is not the IETF quite; it's a little sibling, but doesn't produce standards. So we're trying to do research, and in this case on formal methods and how could we make them more usable. And we have an agenda. You can see it here. So Osama, and then Felix and Corey, and then Deirdre, and we had 100% of speakers, so we're doing well. Any agenda bashing? Did you want to say hi, Jonathan, or anything to the folks while I swap the slides?
Hi, folks. Looking forward to some interesting talks today.
I have to add the clicker, so give me 1 second. Okay, you should be clicker enabled.
Okay, very good. Yeah, thanks very much, especially to the chairs for organizing this on a short time request. I saw that the deadline was coming and there was no UFMRG notification, so I reached out to them. Thanks very much, and specifically for arranging it just before SEAT was very specifically very helpful, hopefully, so that we can talk about proofs here and then say in SEAT that we have already talked about it and just show the results there. That's the plan. So, and thanks to all of you who have been supporting us through the years. So the SEAT working group has been now formed, which means that now we have a lot of work to do. And this is kind of a continuation of the last talks that I have been giving in the UFMRG. So I'm not going to show you that, hey, these are very nice proofs. We have actually some problems which we want to discuss and to see how we can proceed this work forward. So I want to start by thanking Peg Jones, GenXT, CCC, and Teleport who have helped me to be here. The outline is I will talk about the general approach, very high level, and then describe you a little bit about the formal analysis we have done for the attested TLS protocols. And then on backup, I have some slides in case there is any specific question about that. Approach. So what we have done, like formal methods, typically we have security goals. In formal, we start with some kind of use case or some requirements and then try to somehow formalize them in some way, which is the upper part of the chain. And the lower part is that somehow in parallel, we also start trying to build the protocol that what we actually want to do, right? So this is pretty much familiar. What we have done extra is the second block on the top, which is in addition to informal security goals. What we did is like in the last meetings, there was a lot of interest in, hey, what does it mean in the lowest hierarchy? What does this property that you are showing, what does it mean here and there and all that? And we explored very deeply into Loewe's hierarchy, which actually is not correct in our opinion, which I will show you in the later slides. And then the third block, logical formulas, is just a kind of an um, informal thing, because we do not have any semantics, sort of very formal semantics attached to it. It's just a bridge between how engineers see it and how that could be bridged over to something very formal. So it's just see it as a bridging thing between engineers, so that they can better understand what we are doing in the formal methods. I talked to various engineers about it, like they really like the concept. And the main thing about here is explanations in English. What does this formula actually mean? And secondly, the visualization. I will show you in the next slide one example which they really liked, that we show them different traces, that this formula actually means that this is a valid trace and this is an invalid trace. So if you see this valid in your traces, if everything is valid, so your trace is going to be a proof. And if there is a single invalid trace in there, which we depict pictorially, they can see that, okay, so this was a problem in that protocol. And then we go a next step, which is on the attack. If there is an attack, we show them visually that what does it mean, because the attack Proveris shows is like so big that you cannot even visualize what's going on. For engineers, it's impossible to, even for me, like when you have TLS, you have attestation combined together and you see an attack. Now it takes me a few days to decipher what does that actually mean in terms of each and every bit to see what went wrong. So that's the problem. So the visualization really helps them to understand what the protocol problem is. And luckily, like all of my co-authors are engineers, so I already tried on them to see that what's your feedback, how to improve it, and so on. It has gone through some iterations. The lower part is about specifications. The particular thing here is that we have designer in the loop, which means that I talk to the designers that, hey, this is what I have, and tell me what can be improved and so on, so that they are in the loop. It's not that I just throw over the formal proofs to them to give them that, okay, so you have a proof or you have an attack. It's that they kind of work with me in order to refine it. That's what I mean by the protocol designer in the loop, which is to say that they are actively participating in the protocol design together with the proof, and not only just passively saying that, or passively taking that input that, hey, this was actually correct, or this was actually, there was an attack, but they actively see and participate in it. Protocol diagram we make then and apply it by calculus as before. So nothing very fancy in there. What we do is, in addition, we add explanations that in English, that what does it actually, these formulas mean. And I sent over in the mailing list a preprint for that. Hopefully this can be useful as a training material in the future. So what we introduced is a correlation property, which doesn't fall very nicely in the Loewe's hierarchy, or so to say, and also in our hierarchy, we believe, which is to say that if the client, and I use a client and server in the sense of TLS, but of course they are more generic, initiator and responder. If you want, I could also argue that initiator and responder is also a specific terminology. For instance, in the ad hoc protocol or SPDM protocol, it's not a generic term, so to say. So they are also protocol specific. Anyway, if a client and the server agree on the first parameter, which is to say E1 of X and E2 of X, so they both agree on X, then they also agree on the second parameter, which is the interpretation basically, or the explanation of this formula, which is easy to understand that what's going on. And this is the visualization, which is a bit small, but the idea here was to show that which are the traces which actually satisfy this formula, and which are the traces which actually are invalid, which are shown below. For instance, if I see a trace I, which means here that E2 of AB and E1 of AC, the first parameter, they agree on A, but they don't agree on the second parameter, which is B and C. So that's one counter example. If that is in the trace, that they will know that this is actually a counter, not a valid trace. So this is the hierarchy we have in comparison to Loewe's hierarchy. In the next slide, I will compare with Loewe's hierarchy. The idea here is that the upper table basically is for the engineers to see what that is. Basically, aliveness means you agree on a server and the client agree on the server's identity, and not necessarily on the protocol parameters and one-to-one correspondence in the. Yeah.
Do you want people just to ask questions as
Sure,
you go?
sure.
Or?
Yeah,
so
sure.
if people
Feel
want to ask questions as you go, because I have one.
Yeah. Okay,
on
sure,
the, on
please.
the previous slide,
Yes.
can you just say a bit about how you made the visualization and how it appears, other than on a slide? You know,
Right.
how did you show it to engineers?
I started with the initial set of traces that I had in my mind. And then I kept thinking that what would be a unique trace to add to this, which will give them more insight. And I encouraged them to ask questions that whether they think this trace should be valid or invalid. Rather than showing them this whole thing, I showed them a trace and said that, what do you interpret from this, whether this will be valid or invalid. So some of the traces, for example, if you see G, so they thought that this should be invalid because it is AB, 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 that is repeating. And that's what I said, that no, repetition is not a part of this. It should only say that if the first parameter they agree on they always agree on the first parameter, they always agree on the second parameter, and that's not an invalid trace. So I kept showing them to different engineers, and I kept like thoughtfully visualizing, but I do not have a proof that these are the minimal set of you may have more examples. That's what I mean to say. They're not exhaustive.
Sure.
But I would be very happy if someone can intuitively think of more that are not covered. That's what I came up with.
And did you have some tooling to generate these this
No,
visualization, or you just
no, I manually just draw it.
Okay.
So that would be very interesting future work to kind of do some automation here.
Thank
Yeah,
you. Thanks.
welcome. And feel free to jump up to the queue if you have questions. Aliveness, one-way non-injective agreement. One way specifically we say because in attestation we could have a single party as an attester. That's a very typical case. You don't necessarily need to have a mutual attestation. And there Lewis hierarchy actually fails, which I will actually show you in the next slide. And in addition to server identity, it also agrees on the protocol parameters. And then injectivity, so to say, is one-to-one correspondent, that there is no replay attack. And on the bottom, that is more for the formal people, which is to say that implication kind of, but I say general at the top, so to say that it's not 100% applicable in all the cases. It's very much dependent on what parameters of agreement do you have, and also like what is the placement of the events. So this implication is not necessarily always the case. It's general, that typically it applies, but not necessarily always. So typically what we will have is recent one-way injective agreement will imply the one-way injective agreement, and so on. You can add recentness to all of the ones above so that you can move towards the right, and levels 1, 2, 3, they are now shown implied towards the bottom. So Loewe's hierarchy defines weak agreement as what is shown on the slide. Everyone here, I assume, knows about this. What I want to discuss with the research group is, what do you think are the two perspectives? We have thought of both, and both seem to say that, okay, so Loewe's hierarchy is not correct. And I want your opinion on what do you think about this. The first opinion says that weak agreement is stronger than a one-way agreement, which I showed you on the last slide, that the one-way, let's say the attester is the one being authenticated, as it requires the responder to agree on the initiator's identity, which you cannot do in one-way agreement because it's only the one thing that is being authenticated. And the second basically says that no placement of actions E1 and E2 can satisfy the formula 2, which is shown below, which says that for all IDS server's identity, IDC client's identity, action E1 with these two identities implies action E2 with these same identities, that they both agree on these two identities. For example, think of the TLS protocol or ad hoc protocol. Both protocols do not have, server doesn't have any guarantee at all about the client's identity if that is not authenticated. And by no means it can know what the client identity is, then by no means it can just agree on these identities. And that's where we believe this is incorrect. Jonathan.
Can you hear me? There you go. So this is actually just a weirdness of the terminology used by Lowe. So if you're doing unilateral TLS, right? So the client is anonymous.
Right.
What it means by IDC means you are talking to the same person you were talking to before. It doesn't necessarily mean you know who they are. It just means you know, okay, here's a good example. I do unilateral TLS with an anonymous client. If I then do a resumption, I don't know who the client is, but I do know that it was the same client. And so that's what IDC means here.
But when you say the same client, you have to know something about that client to be able to say that
Yeah.
this is the same
So the
client.
thing that you know
What would
about that
be?
client is that it knows the secret. And so the client is the thing that knows this secret.
But which secret?
That's
For example, for TLS, which secret it will be? That is, do you mean the GXY?
well, actually, it's literally any of the secrets in the key derivation probably establish it. But for, just if you think about it like this, you could say, it's the master secret. That is completely a valid way of saying, I'm talking to the same person. The person who knows this master secret is the same person because they know the master secret. So it's not that it's wrong. It's that the identity isn't bound to a name, which is not the same as being not the same identity.
Okay, thank you.
Yeah, hi. So I don't understand your question really. So you have two discussion points, but you also said you think weak agreement is wrong, right? And
Yes.
for me, the statement weak agreement is wrong doesn't type check. It's just a definition, right? You can say it's not the one you want for your protocol, and then I say sure. and I'm,
Yeah, I mean,
I'm fine with
that's
that, right? Like,
that's more of a philosophical discussion. I mean, you can say that, okay, so that's a definition that cannot be wrong, but actually that doesn't apply in many cases. That's what I want to say.
well, I mean, I have looked at least 3 protocols myself. No, 4 protocols myself where it applied. I mean, I don't like what's the thing you want to discuss, right? Do you want to
okay,
discuss
let
whether
me
a weak agreement is the best definition on this planet, or do you want to discuss whether it's the right definition for your use case? And the latter question, I honestly would say, I trust your verdict, right? Like if you say it's the wrong definition for your use case, I say sure, come up with your own.
So what we want to say here is like more of this thing that for attestation, this is not a suitable definition.
Sure, okay.
And
I believe you.
what I want to also discuss is that there are 2 different interpretations. One in the sense that you have a proverif event which is associated with the client and the server in one-way injective agreement, and the other one is the other way around. That is, you have the by two-way injective agreement, and this kind of thing.
Yeah. I mean, one-way, two-way injective agreement. I don't know exactly what this means, so I cannot
So
comment on that.
basically,
But yeah.
okay, we can discuss on the list
Yeah.
maybe. So I have 10 minutes left. Oops. So
just
okay.
one
Yeah.
quick further point. I think what you're looking for, or what you're building towards, is that you want compound authentication, i.e., a proof that the actors in the attestation are the same actors in the TLS connection. And that's the definition you're going to be building towards.
Right. So I have some definitions. I will go towards that. So maybe then that kind of clarifies what I mean here. Okay, formal analysis of attested TLS. This I have shown many times. There are so many attested TLS protocols. What we want to do is to see which one is the best to standardize. And specifically talking about TLS server as an RATS attester. I have a TLS client on the left, physical machine on the right. Attestation key is already provisioned. That's the starting assumption. And then I have something which is called as an attester, which means something that is actually attestable, which you can attest, you can take the measurements. And that is shown as a subset of the physical machine, but not because not everything in the whole machine is actually attestable. So there are like a hypervisor and so on, different software components which are actually not within the TCB. So that's why physical machine is, the attested is shown as a subset of the physical machine. Then there is a quoting agent just to generalize all the technologies, ARM, CCA, Intel, SGX, TDX, blah, blah, blah. That is the agent which will actually generate the quote, meaning that the evidence that will be generated and the entity for which that evidence will be generated is the virtual machine, which means that the state and the public key of that specific virtual machine will be tied together by the private attestation key, which will form the evidence. And there are multiple other virtual machines from other tenants possibly, and we want to also protect from those tenants. That's to say that each VM is the one that we are trying to protect. And in addition, we have something at the bottom, which is actually the identity of the actual infrastructure provider. For instance, if we are talking about WhatsApp, then that's the meta data center that we actually want to get an identity that we are actually talking to meta data center rather than some other machine in somewhere else. And that's where we have the identity IDS associated with its long-term key and signed by the certification authority that will be sent over to that should be sent over to the TLS client. And the way we have organized the properties is like this at a very high level, that there are remote attestation goals, there are TLS goals, and these sub goals we have to satisfy in any case. And then there are composition goals, which I think Jonathan was naming, which is the composition of both, that is providing you the binding between the two goals, remote attestation and TLS. And then we have the informal security goals. I'm trying to explain now each of those set of goals. Remote attestation, integrity and freshness of the evidence, pretty much standard. What we add is establishment of connection with priv, aka the attestation key private part known to the adversary. If the attestation key is known to the adversary, it should not establish a connection. Similarly, for ephemeral key, which was for the virtual machine, if it's known to the adversary, it should not establish the connection, otherwise it can impersonate. And from the TLS side, the standard properties 8446 bis appendix F.1, I think. And then what we add on top is the composition goals. That is, evidence generated by the same server, evidence is generated by the same server that is authenticated, which means that how do I formalize it? It's more like I bind the evidence to a specific TLS connection, and that binding could be in 3 different ways or 3 different levels. That's how I define it, like the GXY, the first level of connection, first level of binding, then the handshake traffic secret of the client, and with which it will encrypt that handshake traffic, the handshake messages. And then the final one, the application traffic secret of the client, which means the one which it will actually encrypt the traffic, the application traffic and the secrets. And on the next slide, I will show you pictorially what do I mean by the levels before that. So GC2 basically means agreement of all remote attestation and TLS parameters, that they basically, the above properties were saying only specific RA and TLS parameters. Now it's combining that they agree also on both parameters together. So that's why they are composition goals. And the threat model here is, as I have shown also in the last meeting, nothing new here. So all of the keys may be leaked, standard TLS threat model. And what I have added explicitly is a set of assumptions that we need from the system, which cannot be taken care of at the protocol level, which is to say that if there is any generation of any problem or weakness in the generation of claims, we cannot protect it at the protocol level. That's a system level property that the system underneath has to guarantee. Verifying relying party is provisioned with the reference values, the measurements that it checks. So we cannot do anything at the protocol level. They have to be assumed to be correct. And similarly, the attestation key and certification authority public part are provisioned already. That's the starting assumption. Then the time of check to time of use attacks are out of scope. They cannot be completely dealt with. Somehow they can be, at some point they can be, or to some extent they can be dealt, but not completely. Right, so here I'm trying to now map them to the security properties, and the weaknesses I have shown, like LAK is the weakness of the attestation key, WH is the weak hashes, and WDH weak Diffie-Hellman, and WE is representing another weakness. So LEK is representing leakage of the ephemeral key. So with all of these properties, we now map them to the threat model, that which property can be satisfied under which conditions. So that's what it is showing. And 3 of them, GCA, 1 ABC, I will show you in one of the slides, that they are corresponding to correlation property that I introduced, which is mapping that if the first parameter agrees, then the second one also agrees. And these are the events, as I said, in the general hierarchy, that which is typical, but it really depends on where we place that these events. And this figure is showing the placement of the events on the server side, and on the client side, all of the events are at the very end of the client, which is shown as client X. All of the events are from the client side are here. Then I have events E1 and E2 on the general formula. The action E1 implies action E2, which I showed. and E1 is showing that what this specific security goal has in that event, and E2 is showing what it is there in the E2. So once we, from the depicted figures, once someone understands what E1 and E2 mean, they can now understand what these formulas are and get a better understanding. And general arguments really mean general in the sense that they are kind of typical, but for a specific property, I may need to somehow manipulate a little bit in order to actually get the property I want. So in general, the remote attestation parameters, as I told you, they have agreement over remote attestation parameters. TLS have over TLS parameters, and composition over both. As you see in GC1A, for example, evidence is from the remote attestation side, and GXY is from the TLS side. Similarly, KCH and KC are from the TLS side, and the last property basically has both parameters. And specifically to show, in this slide, I'm not showing the assumptions which I was showing on, for example, this slide. So I have abstracted them out just to show that this is what E1 and E2 will be. The assumptions will be added when we write specific properties. Okay, with that, for intra and pre and intra, as I showed you on this big slide, big tree diagram, pre, intra, and post, there are three main categories at a top level. And we have done the analysis for pre-handshake attestation and intra-handshake attestation. In the expert BOF, there was shown a lot of interest that why we are going specifically for the post-handshake and why we are limiting the scope only to post-handshake, so to say. So we did a very thorough analysis on all the properties. And as you see, many of the crosses, these are not good for standardization. And we did our next step, which is to say that we tried 5 different solutions to try to reach actually how far we can go with these solutions actually. For instance, we took intra handshake, which is what I show here, 5 solutions we tried. And the best we can do still is that the GC1C property cannot be satisfied, which is to say that basically on shown on this slide, the 3 levels that I showed you, like GXY is here. Second, handshake traffic secret is here, which means it includes transitively the previous contributions. And finally, the application traffic secret is at the real end, which means that it includes all the contributions of the whole handshake, which is the strongest possible binding. But if I want to include it inside that evidence, what will happen is that I need to send that evidence after of 2C message, which is after finished. And then the problem is that I cannot include it in the HMAC of that finished, because finished has already been formed. So you see the cyclic redundancy that we have, that for including, we need to include a log of FS into this ATSC, and then we need to include ATSC inside the evidence in order to create that strong binding. But if we do that, we have to send that evidence after of 2C. And if we send it over there, we cannot include it back in the finished message, which can include the HMAC. So that's the cyclic redundancy. And we believe that it is really hard to solve this cyclic problem. There may be some possible extensions. We are not saying that it's literally impossible to achieve all the properties, but what the best we tried is that it seems really, really hard to achieve this cyclic redundancy and come up with some extensions, which by the way are already out of scope of seat. So we cannot change the TLS protocol, but we went ahead to try to really see what are the kind of the real limits of this. Yes, please.
Rowan Chain, Freedom of the Press Foundation. Thank you so much. This has been really interesting. I wanted to ask, I know we're short on time. I'm coming from the engineering perspective, so I'm less familiar with your methodology, but what were some of the changes you had to make when you were working with the protocol designers to the initial methodology that you sketched out, and what parts are you most excited to develop in the future? Thank you.
So if I understood correctly, your first question is that what did I change in the process?
Like I noticed you had an iterative methodology where you included other designers and engineers. So what was the most part that changed the most there?
Okay, so the most interesting thing was that they could understand better. So the kind of motivation there is that when the so engineers don't get anything other than just say that this is a proof, so go ahead with that, and you might better understand that. So when you are given a proof that it holds, so you need some intuitive understanding of what or if there was an attack, what intuitively went wrong. So that's the kind of visualization and explanation that is added in the process that helps. And could you please repeat the
Yeah,
second?
sorry, the question was just what direction are you excited to go in next? And thank you.
Okay. So the next
So
process is,
I guess so. This will be discussed further in the seat
Yeah.
session, which is immediately following that. So I
Yeah.
guess you can have excitement about the next steps in that. And maybe I know you're almost at the end. So if you could-
Yeah. So can I take 5 minutes? Is it fine for?
5's a bit much.
Okay, okay. So I think I'm at the, oh, even I need less. Okay, so I'm already at the summary. So that is to say that's the protocol designer in the loop approach, which means that protocol designers get more intuition with the help of the explanations, which are in English that they can understand, even if they don't have any mathematical background. And one thing I forgot to mention is that needs really a basic logic level implementation, and the preprint is out there. I will point you to that. And the visualizations are really helpful to intuitively understand what invalid trace means. We believe we identified subtle problems in Loewe's hierarchy, and at least for attestation, that doesn't make much sense to us. We can, of course, discuss it over the list, some opinions that are presented. Then Yes, to my knowledge, SEAT working group is the first working group in IETF, which has formal analysis explicitly written in the charter. And thanks very much for all of you. I think it's a great success for UFMRG in total. And the key insights that we have from all of this analysis is that we need infrastructure identity that I have been emphasizing a lot for quite some time to prevent diversion attacks. And there needs to be a cryptographic binding between remote attestation and TLS. Some people in the expert BOF pointed out that's not required, but I argue that's really required. Otherwise, the whole process is useless. You could have a relay attack which is coming from another server, which is not the one you intended to be. Pre and intra handshake, as I showed you on the crosses on the list, even with the solutions, even if out of scope of seats, still we did extensive effort. We believe still it is really, really hard to solve this problem, if not impossible. Um, and we believe it is one of the most challenging protocols in the IETF because of the hardware architecture details which are included in. And one of the problems, so I explained you the motivation from the engineer's perspective. Another motivation is the people who do. Okay, so we are requesting some feedback on the shared preprints, and we will discuss in the next processes in the seat working group, and that's pretty much it. Thanks very much.
Great. So, and again, if you're interested in this, the seat working group are meeting after the coffee break in Laurier, I think is the room. Thanks, Osama. So next, we have a two-hander. I'll give the clicker some control in a second.
I think here's the best spot. Huh?
Okay.
Good morning. How is volume level? Does that work? Yeah. Okay, great. Good morning. Thank you for being here. My name is Corey Myers. I'm a software engineer at the Freedom of the Press Foundation, and along with Felix Linker at ETH Zurich, we're excited to present a case study in the co-design and analysis of a secure protocol for whistleblower communications. And just for time, we'll take questions at the end. We're going to tell the story in two parts, starting with the motivation and design of SecureDrop as a system that currently exists, and then explain how it's evolving. SecureDrop is a whistleblower submission system that media organizations and NGOs can use to securely accept documents and messages from anonymous sources. It's been used by dozens of news organizations around the world since its inception. As an open source project, it was begun in 2013 by the late Aaron Swartz, and since then it's been stewarded and maintained by the Freedom of the Press Foundation. My colleagues Ro and Julio are also here today and have been driving a lot of this work over the past couple of years. SecureDrop's design is largely unchanged since 2013. We won't go into great detail of the current design, but the interesting thing to note here is that it is not end-to-end encrypted. Messages are encrypted in transit via Tor Onion services and on disk via OpenPGP. And the motivation for this design, and the reason that we think this has been justifiable as an approach over the past decade, is that really the fundamental goal of SecureDrop as a system is to raise the cost of compromising the server by moving the attack from one domain to another. from technical to physical security to legal compromise. The way we achieve that high cost of compromise is to require news organizations to host their secure drops on physical servers in locations they control. To just give a sort of straw man example of why that's useful, in the US, for example, it would be a big deal for the FBI, the Federal Bureau of Investigation, to raid the offices of the New York Times over a suspected leak case. They could do it, but it would be a big reputational risk. They'd have to justify it legally, and it would set off a legal battle. Although Secure Drop is open source and anyone can download the software and install it, we insist on this approach for any Secure Drop installation that we provide support to as a way of enforcing that escalation of cost. At the same time, we know that this requirement is a burden for many news organizations, and we want to broaden Secure Drop's accessibility. We want more journalists in more kinds of environments to be able to use Secure Drop to receive tips and documents securely. For example, what about news organizations that can't afford hardware or don't anymore, especially after the pandemic, have a physical office where they can install it? What about news organizations who don't have a Linux systems administrator to run 2 servers on a firewall? What about news organizations based in locations where this is actually the wrong threat model because physical security can't be counted on and legal protections don't exist in the way that Secure Drop was originally designed for in the US context? What about individual journalists who may be primarily publishing on Substack out of their home offices, but nonetheless are doing work on the national scene and want to be able to receive tips securely from anonymous sources? Our own research and lots of feedback over the years suggest that this accessibility goal really reduces to the question of how a news organization can ask a third party to host a secure drop for them. That might be in the cloud, it might still be physical servers, but in either case, it breaks our model, our assumption that you're running physical servers in an environment that you control. And the table stakes technical question there is how can Secure Drop be end-to-end encrypted? So we began thinking about this a few years ago and abstracted some requirements from how Secure Drop has actually been implemented and deployed over the past decade plus. A newsroom is going to run a server. It's going to enroll some number of journalists for whom this kind of reporting line is relevant to their work. The server will be accessible by Tor Onion services so that we inherit Tor's anonymity properties. Anonymous sources will connect to the server via Tor browser. They'll get a passphrase that is their only piece of state for that session. They'll send messages. In Secure Drop, it's currently deployed, and in future work, they'll be able to upload files. That's out of the scope of what we'll talk about today. And they can return to the server to reply to other messages they get back from journalists. The journalists who are enrolled then can log into the same server. They can retrieve messages. They can download files in current and in future work, and they can reply to messages. As we looked at these, we found that there were some implications from these requirements that were not immediately obvious. One is that we consider Secure Drop to be a solution to a kind of first contact problem between people who are highly visible and well known on the internet and want to be contacted, and anonymous parties. And that effectively means that all key distribution for this system has to be in-band. For journalists, that means that their keys are publicly available, and so sources download them and can encrypt messages to them. For sources, they actually enclose their keys in messages to journalists so that journalists can reply back directly to them. Sources have no persistent state between sessions. We'll come back to this. Each conversation is one-to-many between a source and however many journalists are enrolled at the time. Conversations can be highly asynchronous. And that means that we can't rely on any system that depends on participants being online at the same time, either for the initial bootstrapping and key agreement, or for actually having a conversation. And we want to trust the server as little as possible. So we want to minimize the amount of metadata that the server holds at any given time, apart from the messages themselves. Now, looking at these requirements, you might well ask, especially in this crowd, why we're not just using Signal or MLS. And we thought about this a lot. We actually did some prototyping work a few years ago to look at an implementation of the Signal protocol for this purpose. We consider it best-in-class secure messaging. Signal in particular is a staple of the recommendations that our colleagues on our digital security training team make to journalists about how to secure all the rest of their communications. And we knew that groups could accommodate one-to-many messaging from sources to journalists. What we found, though, was that a few of these requirements in particular wound up violating things that we needed. So for both Signal and MLS to do key ratcheting, you need some kind of app or session with persistent state to ratchet keys. And that violates our requirement that sources have no persistent state to actually run the protocol across sessions. The alternative to that, you can do something clever with opaque. You can encrypt your current session state and store it on the server. And that way the client doesn't have to store it. The client is still stateless, but then you've created very persistent evidence on the server of this session, whether or not there are messages associated with it. For Signal or MLS in large scale deployment, this is a non-issue, because if you're looking at millions of messages a day, having visible on the server session bundles doesn't mean anything. If you think about this as a very low volume, high stakes messaging service, where the presence of even one new, in this case, a source session bundle means that a new source is connected to the server, that's actually highly revealing metadata in its own right that we wanted to minimize. So we began looking at this again in about 2022. My colleague Julia was leading a lot of this work at the time, and began looking at what it would look like to do an end-to-end encrypted messaging protocol specifically to satisfy these requirements. In 2023, we had a first proof of concept that laid out some of these security requirements on this threat model, a first draft of the design, and an increasing wish to be able to do some kind of formal modeling to prove, given the stakes, that we were actually going to achieve the security properties we wanted. As luck would have it, we've been going to IETFs for a couple of years at that point. At a 118 in Prague, Felix gave a workshop on the Tamarin security protocol verifier operating in the symbolic model, and Julia and I were there and thought it would be a pretty good fit for the kinds of analysis and modeling that we wanted to be able to do. So we attended the workshop and immediately found that as soon as we modeled the protocol, we couldn't get Tamarin to terminate. We knew immediately why, which is that the most novel part of this protocol relies on the commutativity of multi-party Diffie-Hellman key agreement, and that immediately led to a state space explosion in Tamarin that we couldn't manage, and it turned out in short order neither could Felix right away.
Yeah, and that's where ETH Zurich came in. So I must admit, I would have loved for Tamarin to work out of the box for the Freedom of the Press Foundation. But on the upside, that not being the case led to a great collaboration for us at ETH Zurich. So when the Freedom of the Press Foundation approached us, telling us, hey, we have something for you, they actually came quite well prepared. As Corey said, they already had security requirements, they had a threat model, they had a design, and certainly they had a strong desire for formal analysis. And this is what I'm going to talk about in the second half of this presentation, the formal analysis that we conducted of the SecureDrop protocol. So the work that we did as a team was really an iterative process of taking all these three inputs, the security requirements, threat model, and design, formalizing them both in the computational and in the symbolic model. So doing both pen and paper proofs, more on the cryptographic primitive side, and doing symbolic proofs using the Tamarin prover more on the protocol level side. And out of those formalizations, we typically got output that suggested there is a room for improvement, or maybe there is a flaw. We took those outputs and then informed a new iteration of the security requirements, threat model, and design, which we then again formalized in those two models. So in the rest of this talk, I would like to talk about all these aspects to finally give you a quick sketch, way too high level sketch of the properties that SecureDrop achieves. So SecureDrop was designed to provide 4 security requirements. Earlier, Corey already talked about the functional requirements that the system has. Now let's talk about security. So first, evidently, the messages exchanged over SecureDrop must remain secret. So SecureDrop has a requirement for confidentiality. Second, also quite clear, we have the requirement of anonymity. Sources using the system must remain anonymous when doing so. Then third, this is not such a common requirement. The clicker doesn't work. Oh, no, it works. Yeah, we have the requirement of undetectability, which means that messages should be not visible to the adversary in any way. They shouldn't be able to, for example, count messages. They shouldn't be able to see the timing of messages when they're exchanged. And finally, we have the requirement of authentication. Sources and journalists in their communication should be able to do so authentically, being assured who they're actually talking to. SecureDrop aims to provide the security requirements in a very complex threat model. For example, we consider that any of the parties using the protocol could become compromised during the protocol run. Sources could be compromised by, for example, leaking their passphrases, or it could be that an adversary simply mimics a source by connecting to the SecureDrop server themselves. The server is now hosted in the cloud, so compromise of it must be considered as well. And journalists could reveal their key material, which could lead to the adversary impersonating them. In particular, for the server, we would like to distinguish between active and passive compromise. Both scenarios are possible, but the passive case is much more likely, and we would like to understand exactly what happens in this scenario. And naturally, we're also concerned about adversaries that may obtain quantum computing capabilities in the future. It was clear to the Freedom of the Press Foundation from the beginning that a SecureDrop design will probably not be able to provide all these security requirements against all adversaries to the full extent. One outcome of the formal analysis is that it helped us to be precise which security guarantees precisely are guaranteed against which adversaries. But to understand that, you first need to understand how the SecureDrop protocol works. So now let's talk at a high level about how this works. So at its core, the SecureDrop protocol uses two cryptographic primitives. There are more, but I'm introducing these two now only. We use a standard public key encryption scheme, PKE, that just does public key encryption. And we use a second public key encryption scheme that is authenticated, and we abbreviated that with APKE. And authenticated means that you can verify which sender generated a ciphertext. We combine both these encryption schemes into a message encryption scheme, the ciphertexts of which are then exchanged over a message delivery protocol that runs over Tor. Let's take a look at some details. In the message encryption scheme, senders generate two ciphertexts. First, they use the standard public key encryption scheme to generate a metadata ciphertext. With that ciphertext, they encrypt the sender key. Second, they use the authenticated public key encryption scheme to encrypt the actual message they want to send to the recipient. The key for authentication of the APKE is the one they encrypted in the first ciphertext. They take both these ciphertexts and then want to evidently send these to the recipient. For that, they use the message delivery protocol. How does this work? On a high level, unfortunately, we have limited time. So in the message delivery protocol, the sender would like to send a ciphertext anonymously and undetectable to a recipient. They do so by uploading this ciphertext together with a clue to the server. The server simply stores the ciphertext and clue for later use. Recipients can contact the server and ask it whether there are any messages. When they do that, the server generates a challenge based on the clue, and if the recipient successfully solves that challenge, they are given the ciphertext. Critically, the clue reveals nothing about the recipient to the server, and the challenges are re-randomized with every request. This allows the message delivery protocol to provide both anonymity and undetectability to outsiders connecting to the server. Now let's talk about the formal analysis. In our work, we provide proof for all four security properties that SecureDrop provides. We provide proof for anonymity and undetectability in the computational model doing pen and paper proofs. For confidentiality and authentication, we split our work into primitive level proofs that are carried out in the computational model, doing again pen and paper proofs, and protocol level proofs that are carried out in the symbolic model using Tamron. From the interactions of these two worlds, we took away that the computational model really helped us finding the best abstractions for the different building blocks that we use in the protocol, whereas the symbolic model using Tamron helped us detect regressions in our iterative analysis loop. And Tamron's support for machine check proofs really helped us there. What I find particularly neat is the handover that we do between the computational model and the symbolic model. And I'd like to give you an intuition for how we connect computational and symbolic proofs next. But before I go into that, a quick footnote. So I said we connect, there's a handover. The guarantees we have there are not formal. It's more a methodology of how to approach the verification. So let's take the authenticated public key encryption scheme as an example. Under the hood, this authenticated public key encryption scheme is using the HPKE RFC in the auth PSK mode. So we could reuse some guarantees, but we found that the proofs that have been done of this public key encryption scheme weren't quite there where we needed them. So Shannon, the lead cryptographer on our team, proved the two guarantees insider CCA and outsider authentication of this cryptographic primitive. The first guarantee intuitively means that the adversary cannot learn anything about messages being exchanged, about the contents of the messages being exchanged, and authentication means that it's hard for an adversary as the outsider to generate ciphertexts. In the symbolic model, what one would typically do is write equations that define how encryption and decryption operations interact in the symbolic model. These equations hold unconditionally and can be used always. We didn't follow this approach, but instead axiomatized the computational guarantees that were proven in the computational model. We write properties that relate decryption events to the structure of terms and other preconditions that are required. This approach was pioneered by Cas Kremers and his co-authors, for example, in papers like Keeping Up with the Chems. This axiomatization approach allows us to explicitly capture the assumptions that the computational guarantees of the cryptographic primitives rely on. If they hold, things go well and the protocol is secure. But if they don't hold, all bets are off and the adversary can, for example, choose the result of decryption events. The benefit of this axiomatization approach is that it provided us with a clear separation of concerns. Shannon, the cryptographer, could focus on the computational guarantees of the primitives, and I, together with Luca, could focus on the protocol level security guarantees in Tamron, and we had a straightforward, not straightforward, but we had a clear methodology, a clear set of steps to take when deciding how we model the cryptographic primitives in Tamron. And moreover, this is a more accurate model of the cryptography. Some findings that we, so these are some example findings that we got from during the security analysis. So with this methodology, we found an attack on the message delivery protocol during the design that was actually quite simple, but it went unnoticed for quite a while nonetheless. And in particular, the precise model of the cryptography in the symbolic model made us stop making claims on protocol level replay protection guarantees because the computational guarantees that Shannon proved on the primitive level weren't quite there to allow us to prove replay protection on the protocol level. But as a footnote, SecureDrop as a system overall will still give you replay protection, just not provably on the protocol level. With that, let me show you our results table and which security guarantees the protocol provides. So at the end of the formal analysis, we found that it's best to distinguish between these three adversaries for the security guarantees. We have an external adversary. This would be someone like you and me, simply connecting to the SecureDrop instance and doing whatever. We have a passive server adversary who, for example, obtains a disk snapshot of the server running in the cloud. And we have an active server adversary that, for example, could also deviate from the server message delivery protocol. You see here a couple of atom footnotes. This means that the security guarantees are degraded against the harvest now, decrypt later adversary with post-quantum security, with quantum computing capabilities. So next, let me give you an intuition for why certain things do not hold. So for undetectability, we cannot provide this property against a malicious server because the server is given the ciphertexts and stores them in the database. So this attack is quite straightforward. There we cannot provide this guarantee. For anonymity, an active server can identify the public key of a recipient by deviating from the message delivery protocol and doing some funky business there. And for the post-quantum security guarantees of undetectability and anonymity, The message delivery protocol is not post-quantum secure right now because it relies on the commutativity of elliptic curve Diffie-Hellman. So an external adversary in particular, for example, could regularly query the server and then find out which public key received messages at what times. Also, you see that we have all these green check marks for confidentiality against all adversaries here, and that is true, but this is actually way too simple than what the protocol provides. There are very subtle and different guarantees based on the parties. So there are different security guarantees for sources and journalists, and with different notions of forward secrecy and post-compromise security, both of which are provided by SecureDub. Yeah, but for details, find me in the hallway later. So we decided that it's best to have two sets of conclusions, one from the ETH Zurich and one from the Freedom of the Press Foundation side. And I would like to start with the ETH Zurich conclusions. I went into this project already believing that everyone should formally analyze their protocols. And it probably comes to you as no surprise that the collaboration, it was really fun, and I learned a lot to reinforce this belief. In particular, this was a learning for me. I saw in this particular case study how you really need both a computational and a symbolic analysis. And I think we provide a great case study for how to combine them practically. Also, as a footnote, let me say that many details of SecureDub, the protocols and security guarantees were not covered. So this is a formal invitation to nerd snipe me on the hallway. I cannot make this invitation on behalf of the Freedom of the Press Foundation, but maybe you do it.
Please do. Yeah, we really just wanted to model it in Xamarin, and that was 2 years ago now. It's been a great project. It's also been an enormous effort on all our parts to make this happen. But I think the benefits have been greater than we expected. We thought we were going to get proofs. We wound up getting this two-phase, two-mode set of proofs that I think have also let us iterate on the design faster because we've had the confidence of both ETH Zurich's expertise and these tools to sort of backstop decisions that we make both at the primitive level and at the protocol level. I think all I'll say, just to leave time for questions, is all of this sort of in parallel with the distinction between the symbolic and the computational proofs that Felix mentioned. We're assuming implementation with verified primitive libraries. We're looking at how to then couple our implementation with some kind of verification to the model as well. And so we want to reuse as much of this proving work as possible as we proceed towards implementation so that the implementation inherits the guarantees that we've been able to prove. Thanks.
Thank you. So I think we have a few minutes for Q&A because there's a bit of slack at the end. So join the queue if you have questions or comments. Thanks. Osama?
Right. So I have two questions. First, from the contribution perspective, like there are already some works like for TLS 1.3, it was already done that you have computational proofs and in together with symbolic proofs. So was there a specific contribution that you claim here in your approach specific to, let's say, the existing work on top of, or was it just a case study that you did for this work?
I would say it's rather a case study. I'm not saying, like, for example, the way that we model cryptographic primitives is 100% inspired by how Kars Kremers did it, right? I don't claim any novelty here.
That's fine.
Yeah.
Yeah, that answers my question. So second one was more for Corey. So what was your kind of background? Can you share with us some of your background? Are you like formal methods? Were you already familiar with formal methods? I'm trying to see what was the kind of takeaway and what was your background and other people from your freedom of press. Was there someone already familiar with formal methods? I believe, at least from my experience, Xamarin is not very easy to use for engineers.
Yeah.
You really have to really, so what was your background? Can you share with us?
We're a software engineering team and in many ways new to protocol design in this sense. The motivation was pretty strong to use both the best techniques and the best tools we could find if we were going down this path. But it's definitely been a learning curve for us and has certainly pulled us more in the direction of using these tools, but with that learning curve for sure.
Right. So you did not code with him. So he was coding and you were just kind of in the loop like the one I showed. So you were kind
of the split has been very much proving labor versus engineering labor so far. Yeah, between our two organizations.
Jake?
Hi, I'm Jacob from Carnegie Mellon. A few questions. How big was your model in the end?
I don't know. I'm sorry. You could take a look. I think it's like 300 to 500 lines of code maybe, but that's really just yeah, I don't remember. I mean, it's also hard to measure, right?
Yeah.
Do you want to know lines of code, number of state transition rules, number of auxiliary lemmas? I would encourage you to take a look. Sorry.
Cool. And have you considered trying doing the anonymity and the undetectability proofs in Tamarin?
Yes, we have considered that, and Tamarin has proof for properties of observational equivalence. I played around a bit with it to have. I was already quite convinced that it wouldn't scale because these properties are just computationally, like from the from computing point of view, are harder to prove. But also, I found out that. So yeah, to give an intuition, proofs of observational equivalence in Tamarin basically mean like if you change just one piece in your protocol, for example, you change one public key to be a different, can the adversary tell these two worlds apart? So this sounds a bit like anonymity undetectability, maybe, I hope, to you. But the problem here is that the notions of when the adversary can distinguish two things, in my view, are too strong. So I found like I couldn't actually prove the guarantees I wanted to. Yeah.
Interesting. And have you running into the termination issue? Have you tried? Or did you try using a different prover like a Proverf? At least personally, I've had a better experience dealing with the commutativity of a Diffie-Hellman in Proverf than Tamarin.
Yeah, but I think that's because Proverb doesn't support commutativity fully, right? I'm not
Yeah.
sure. I don't know all the details of the equational theory between Proverif and Tamarin, but I think that Tamarin is a bit more accurate in the Diffie-Hellman model. So yeah, it makes sense that if you have a simpler model, it terminates faster.
Yeah, makes sense. Thank
Yeah.
you.
Oh yes, and then also yeah, this I think this is a cool insight probably for the audience. Thanks for pointing it out, Corey. So also the Freedom of the Press Foundation benefited from experience from people like me because I actually did implement an optimization into Tamarin because while doing the proofs, I noticed that a couple of cases that Tamarin did consider were really like in German we say Quatsch, like just stupid. So I sat down, thought about formalizing why this is stupid, and I noticed that you can integrate a pre-computation step to rule out a bunch of these cases. So I implemented that proof that that this is actually a sound optimization, and then everything went much faster. So yeah, it helps having people who can do that, I presume.
Okay. And quick, if we can be quick, that'll be great.
Of course, yeah. Antonio Vicente. It might just be a naive question, but anyway, have you tried to do anything to actually try to address the undetectability and anonymity problems that you actually have in the active servers? If you actually like consider like some of the things that like Tor and other systems are actually done, actually like adding dummy messages as a way to actually like add enough noise to hide real messages.
Yeah, we're aware of those gaps between what we get from Tor and what we get at our messaging layer, and we'd love to talk more with you about that offline. Thanks.
Great, thank you. That's great. That's thank the speakers. It's nice to see a marriage that was started at the research group. Thanks, UFMRG. Okay. I'll give you clicker stuff in a second.
Cool. Microphone for short people. Okay, hi, I'm Deirdre. I'm going to give an overview of the Proof Ladders project, which is a kind of little project that spun out of the High Assurance Cryptographic Software Workshop called HACS that I help organize. So you wouldn't write your code without a computer. You wouldn't write LaTeX without a computer. Please go forward. Computer help write proof. This is not news to this room, but I'm reusing slides from a previous talk. Apparently this is a novel thing to bring to a bunch of purely theoretical cryptographers. They're like, wait, I can have computer help me write proof? Yes, computer-aided cryptography to help use formal methods, to help prove cryptographic properties in the computational model, symbolic model, and about implementation properties of actual code. Here's our EasyCrypt game. We haven't been doing a bunch of EasyCrypt today, but if you want to get down into your computational properties, EasyCrypt is kind of the most hardcore, will let you do almost everything you can do in pen and paper with a computational model. We have our ProVerif proofs. We've seen some of those today about how to do kind of protocol level properties, post-compromise security, forward security, things like that. But we have a lot of tools. So that's two for two different computations. There's a computational model and a symbolic model. There's a lot more. What if you want to learn how to actually prove stuff with some of these tools, but which tools do you start with? If you're familiar with writing proofs in a certain way, is there a tool that lets you do the thing that you like, or is there a better way to prove stuff, maybe an easier way, a nicer way? And like, how do you do that? Proof techniques, not just I would like to prove security about a PRF and then a hash function and then something based on that. And then I build up a protocol. I want to learn the techniques using these tools, not just how to build up more and more complex cryptographic or protocol constructions. So we've started this project called Crypto Proof Ladders. It's a collection of different ladders to work up how to compare and contrast some of these tools and approaches of how to actually do computer-aided cryptography in different settings. So we have a ladder for symmetric, a ladder for asymmetric, a ladder for protocols, and we have a ladder for implementations that's not listed on the website yet. Of these, the protocols one is the most robust, and so I'll probably talk the most about that today. This is supposed to be a gentle-ish introduction to formal methods for cryptography. It's generally targeted at a working cryptographer more than a broad, maybe protocol level IETFer. But anyone can, in theory, use it. It's like you don't have to, be a card carrying cryptographer to just use these tools. They're all the ladders. They're all on the internet. We're trying to ramp up in proof technique difficulty rather than construction complexity. And yeah, we're trying to meet different audiences, but no one particular audience. I will say that all the techniques and proofs and everything like this has been heavily influenced by a bunch of cryptographers, less kind of broader formal methods people. So that's highly influential there. So I'll give a little tour. The protocols ladder is definitely the most robust. So this is the ladder we have now. We start with a basic hash construction, and then we do signed DH, signed chem, signed DH and chem, a simplified NTOR version, like the one that's actually used in the Tor protocol, and a simplified ACME protocol. I'm not going to show I was going to try and show like an example of a proof for each step on the ladder, but we have a lot of them, so I kind of can't do that. So for basic hashes, we have some from Squirrel, CryptoVerif, EasyCrypt, Tamarin, ProVerif, and DY star. And we don't have DY star for some of the more complicated ones, but we have proofs for almost all the other tools for every step in this ladder. And yeah, they're all on the website. They are quite nice. They're all linked from the website. Probably the best place to actually go find the actual proofs is on the GitHub. So we have 4 different repos that collect per ladder all these proofs. We try to make sure that they still compile. The CI for all the proofs is okay. It needs to be improved, but they were all working as of a couple of months ago or a couple of weeks ago. The asymmetric ladder exists. It's smaller. We have one problem, which is the security of a chemdem, and we have a proof in EasyCrypt, and we have a proof in ProofFrog, which is a slightly newer tool that's trying to have like a much higher abstraction of how you model games and primitives and instantiations of those primitives, and then doing game hopping rather than kind of being EasyCrypt is very deep in the weeds. You can do game hopping, but you have to kind of build the abstraction yourself. ProofFrog is trying to abstract a lot higher. I like it, but it's a brand new tool. Um, and we have, I think, two problems in the symmetric ladder. Yeah, we have a PRG, which is implemented EasyCrypt, and I think Encrypt them Mac is also an EasyCrypt. And we have one thing for implementations, which is long subtraction. We have it in Bedrock, Lodestar, Hax, and Jasmine. Um, we're not exactly sure what else we want to put in the implementations ladder yet, but there's a lot of interest in things like proving panic freedom and proving that secrets will always be independent, computed over independently of runtime and things like that. That are popular in some high assurance applications and has been done again and again, especially with the Hax toolchain and FStar. So please go check it out. Again, the repositories on GitHub are probably the best place to just enter and go exactly to where I've just demonstrated. We are trying to make this a bit of an open org sort of thing. If you have interest or want to see different problems added, we're interested in ideas. We've already accepted some submissions for third parties being like, oh, I did this problem, this step in the ladder, and I did it in this tool. That's how we went from like a handful of implementations on the protocols ladder to like 7 for each problem. This is a big collaboration with a lot of people. I'm just the one up here talking. I especially want to shout out Trevor Perrin, whose idea was this whole brainchild. But all of these people have contributed work to make all of this stuff happen. You wouldn't write a proof without a computer. Learn to walk the proof ladder. So.
Thanks very much. Very nice work. I really like it. And one question specifically from IETF perspective that I have is, if I understood correctly, your main focus was cryptographers, and you want to use them to use computer-aided tools. And how far is the progress from engineering perspective? Like, are you still considering that to from IETF perspective, like from UFMRG and IETF perspective, to target the engineers, kind of make the training material or some ladder like this for engineers? Is that in scope or out of scope or not a focus?
I wouldn't say it's out of scope, but for anyone who writes proofs, and usually they're writing them in a paper, pen and paper style, and we want to give them a taste of what you can do with a computer aided tool in the different, symbolic models, computational models, or like, there are some of them like Squirrel, they're kind of 1 foot in each world.
But just to clarify, my question was more like, I mean, you're saying the ones who do proofs, but engineers don't do any proofs at all. That's
we are targeting people who write proofs,
right.
for whatever purpose that they are writing proofs. So we're trying to be like, so one of the common failure modes of like previous iterations of this sort of kind of ladder approach is like, we're like, okay, we're going to start with a PRF and a hash function and Diffie-Hellman in a group, and then we're going to build up a protocol. And all the cryptographers would come and look and be like, the first step is an interesting thing to prove. Up here at the more complicated level of the cryptographic construction, it's a boring thing to prove. This is boring, but I want to prove XYZ thing, like maybe something involving NCCA of a CAM or a PKE or something like that. Getting from like the second layer to like the 6th layer, there's like this like peak and valley of the proof techniques. I need to be able to do this way of writing a proof, this technique that I use in my papers to write a proof. If my tool can't let me do that, I'm not going to use the tool. It does not help me do my work better. So that's why it kind of went this specific way to be like, if you're a person who writes proofs, here's how to learn the tools, or at least get a taste of using the different kinds of tools and the different way that they prove things and their models and their approach, to see what ones you like, to see what does help you do better work or more verifiable work, and which things are just not your cup of tea. And then if you want to give feedback to the tool authors, just be like, I love this, but I'm used to writing my proofs in such and such a way. I'm used to doing such and such an abstraction and making an argument, blah, blah, blah. It's not supported in your tool. Would you, things like that. So that's the goal, or that's sort of the target audience. But if anybody finds this useful, that's great. If they're learning something from all the material to prove something about an IETF protocol or a change, great. But the kind of goal is to be like, anybody who wants to write proofs is to help them learn how to do it with these tools. That's kind of the target.
Sure. So, I mean, I kind of understand this story, which is very great. What I'm still missing is, let's say I, as an engineer, I want to use this. I have no knowledge of computational proofs at all. I have experience with this ProVerif and the symbolic side of it. Would I be your target audience or not? Can you?
I mean, if you show up and you're like, I like looking at easy crypt proofs or something like that, you could be like, you could maybe use that as an entry point. Like, okay, here is a basic hash security, like, I prove that this is a secure PRF or whatever it might be. Using EasyCrypt. It could also just be your entry point to be like, okay, I get that part, and then you go to next step up the ladder and use a slightly different technique in EasyCrypt to prove something a little bit more complicated. I could definitely see that, because like some of the tools that I'm less familiar, I think Squirrel, like having a ladder, while it's not necessarily a ladder in like, I'm taking building blocks and building something more complicated, like in the construction, the ladder of proof techniques is still going up in complexity and difficulty. It's just going up in proof techniques, rather than like I'm starting with a hash function and I'm building Acme or something like that, or even though there's a little bit of that. So it can be, I think, in theory.
Sure, thanks.
Yep.
Okay, great. Thanks, Judah.
Jonathan, question or?
Oh,
No, never mind. Thank you.
Thanks. Okay, great. So I think we have a bit of time for any other business, or if somebody wants to talk about something else that was happened earlier. Now's a good time. And if you don't, then Osama does.
So not super relevant to this, but I would like some contributions also from this research group. What we are planning is a new research group, which will have formal methods as part of the thing. And we would like to, so the core idea that we discussed in the site meeting was to have it as a research group on the the confidential computing. And like it's not going to kind of provide the training, so it will be kind of orthogonal to this, but we would still like some of the contributions of this research group to that. Yeah, so the core idea is that we will have confidential computing and formal methods. They're focused specifically on that.
Sure. So this is a proposal for a new IRTF research group.
Yes,
yeah.
correct.
Can you send a pointer to, is there a mailing list or?
It's still in progress. So we are having another site meeting today. So anybody interested is welcome to that.
Okay, so if you could send a link to something to the mailing list, that would be great. And then people who are interested could jump in.
Sure, thanks.
Thanks, Osama. Hey.
Hey all, Stu Card, Trusted Computing Center of Excellence hat on at the moment. Just wanted to remind everybody that we exist, that our mission is to push formal methods adoption out there in the real world business community, especially where it involves like critical infrastructure, and we desperately need help.
Okay. Well, if you want to drop a mail to the list saying what kind of help you'd like, maybe somebody can help. As we can see, the Corey's group got help, so it happens. It might take 2 years though. Okay, and with that, I think Jonathan, unless you had anything else, or okay, we still have Jonathan's presentation that's in the back pocket that he's never ever given. So we won't do it today either. So there you go. All right, folks, thank you, and we'll be in touch on the list and as we go. Thanks.
Bye, folks.
Thanks, Shannon. Thanks also, Chris, for making notes, and I'll whack those up into the thing shortly.